Hello everyone, this is the 10th lecture of the lecture series on open channel flow. In this lecture, we are going to discuss about gradually varied flow in open channels. In last few lectures, we have discussed about uniform flow, and we know that uniform flow is sort of open channel flow in which the flow properties, especially the flow depth, remains constant throughout the course of the flow. So that's why it's termed as uniform flow. Now, gradually varied flow in open channels is, of course, it's a non-uniform flow, and it can be defined as a steady non-uniform flow for which the depth of flow changes gradually. The name itself is self-explanatory. So here we are looking at a non-uniform steady flow for which the depth of flow particularly changes gradually. So you can imply from that statement that for a fixed discharge, the velocity of flow varies along the channel. As the flow depth varies, for a fixed discharge, the flow velocity is going to vary along the channel. And that's why, unlike uniform flow, the channel bed, the water surface, and the total energy line, they are not parallel to each other anymore. The channel bottom, that's why the channel bottom slope, the water surface slope, and the friction slope or the slope of the total energy line all are different. This has been shown by the couple of figures at the top. On your left, you can see a schematic of a gradually varied flow in which you can see the water surface is dropping gradually, and so is the energy line. And please note that the slope of the water surface, the total energy line, and the channel bottom all are different. On your right, it shows an longitudinal section in a gradually varied flow where there is a control structure in the open channel. The control structure is a kind of hydraulic structure which is used to control the flow along an open channel for to serve many purposes. And due to this control structure, we can see that the water behind it is backing up, and there is a backwater curve behind the control structure that has been formed. And this backwater curve is an example of a gradually varied flow. As you can see that the depth of flow is gradually varying behind the control structure. And you can see that also a couple of lines, critical depth line and normal water depth, which we will discuss in this lecture later. So with this definition of gradually varied flow, let's try to define or derive a differential equation describing the flow. Before that, let's we have to assume there are a couple of assumptions that we are going to apply in the derivation of the differential equation. And the assumptions are given as: number one, the curvature of streamlines in the gradually varied flow is minor, and thus the pressure distribution at any section in GVF or gradually varied flow is assumed to be hydrostatic. So as the flow depth here is varying gradually, we can assume that the curvature of the streamlines is minor, and that's why the pressure distribution in the normal direction doesn't deviate from being hydrostatic. We know that when there is a significant curvature in the streamlines in a flow in the normal direction, that gives rise to an acceleration in that direction, and the pressure distribution deviates from being hydrostatic. Assumption number 2 is that the resistance equation, like Manning's equation or Chase's equation, what we have studied in context of uniform flow in open channels, those resistance equations are also valid, also applicable for gradually varied flow, provided that we replace the channel bottom slope by the friction slope or the energy slope. So if we write the Manning's equation for GVF, gradually varied flow, this gives V equal to, V is the cross-section average velocity, depth average mean velocity, V equals to 1 by N R to the power 2/3 into SF to the power half. So here, of course, N is the Manning's roughness coefficient and R is the hydraulic radius. And note that the channel bottom slope S0 has been replaced by SF, that is the friction slope or the slope of the total energy line. Similarly, Chase's equation can also be written as V equal to C into root under RSF. So the total energy of flow in GVF in a channel of small slope can be written as H equal to Y plus V square by 2G plus ZX, where which has been shown by equation 1 on this slide. So H on the left hand side is the total energy of flow, and is the summation here is the summation of the flow depth, the velocity head, and the elevation of the channel bottom from the datum, and is given by Y plus V square by 2G plus Z. And note here that unlike uniform flow, here every term in that equation is a function of X or function of the longitudinal distance. H can also be written as equal to E plus Z, where E is the specific energy of flow. Now, if we differentiate equation 1 with respect to X, we arrive at equation 2, which is given as dH by dx equal to dy by dx plus dx of v square by 2g plus dz dx. So here let's look at the terms one by one of equation 2. On your left hand side we have dH by dx, and dH by dx actually represents the slope of the energy line or total energy line or the energy slope, which can be written as dH by dx equal to minus SF, where SF is the friction slope, and minus sign here signifies the fact that the total energy is decreasing in the longitudinal direction. Similarly, dz by dx, the third term on the right hand side of equation 2, represents the channel bottom slope and can be written as dz by dx equals to minus S0. S0 is the slope of the channel, and here again the negative sign is for the fact that the elevation we assume to be decreasing in the direction of the flow or in the longitudinal direction. The first term on the right hand side of equation 2 is dy dx, and here represents the slope of the water surface with respect to the bottom of the channel. The second term on the right hand side of equation 2 can be manipulated a little bit and written as d dx of v square by 2g equals to minus q square by g a cube into dA by dy and into dy by dx. This has been shown by equation 3 in this slide. Here we can write dA by dy equals to t. T is the top width of the channel, and so d dx of v square by 2g equals to q minus q square t by g a cube into dy by dx. This has been shown in equation number 4 in this slide. So substituting all the terms now in equation 2, going back to equation 2 and substituting all the terms, we have we arrive at equation number 5, which shows minus sf equals to minus s naught plus dy by dx minus q square t by g a cube into dy by dx. And if we rearrange the terms and take dy by dx on the left hand side, then we arrive what is called the governing differential equation for GVF, or gradually varied flow, in a prismatic open channel of small slope, given by dy by dx equals to s naught minus sf by 1 minus q square t by g a cube, which is highlighted in blue and is given by equation number 6 in this slide. Now we can write the differential equation in other forms, and let's try to do that here. If we consider K to be the conveyance of the open channel at for any flow depth y, and K naught be the conveyance of the same open channel corresponding to a normal depth y naught, we can write that applying Manning's equation. We can write equation number 7 and 8, which shows K equals to Q by SF to the power half and K naught equals to Q by S naught to the power half. We already discussed that resistance equations which are applicable for uniform flow are also applicable for gradually varied flow as well. So from equation 7 and 8, we can write equation number 9, SF by S naught K naught equals to K naught square by K square. Also, if Z is the section factor for flow at any depth y, and ZC, Z with the subscript C, is the section factor for the flow at critical depth, then we can write by definition that Z square equals to AQ by T, which is given by equation number 10, and ZC square equal to AC cube by TC equals to Q square by G. This is the relation that we developed while discussing about energy depth relationship for open channel flows and the uniform flow. So from the previous equations 10 and 11, we can write equation number 12, which gives Q square T by G A cube equals to ZC square by Z square, and substituting these values in the governing differential equation of gradually varied flow, we can write equation number 13 as dy by dx equals to S naught 1 by K naught by K whole square by 1 by ZC by Z whole square, which is given by equation number 13 in this slide. So this is one form of the equation, and we can actually write in some other form as well. If Qn is the discharge for a uniform flow of normal depth y, and QC is the critical discharge for the same depth, then we can write Qn equals to K into root under S naught, and Qc equals to Z into root under G. These are the again the relations that we used that we have invoked from our lessons in energy depth relationship and uniform flows. And if we substitute again these relations in the governing differential equation 6, then the differential equation can be written as dy by dx equals to S naught 1 by Q by Qn to whole square by 1 by Q by Qc whole square, which is given by equation number 14 in this slide. So from the differential equation for gradually varied flow, let's move on and discuss about some classifications of gradually varied flow profiles. For an open channel flow, Y0 and YC, that is the normal flow depth and the critical flow depth, are two fixed flow depths if we consider that the discharge, the Manning's roughness coefficient and channel bottom slope, they are constant or they are fixed. So given that this statement is correct, there are three cases possible here between Y0 and YC, and those are case number 1, Y0 is greater than YC, or the normal flow depth is greater than the critical flow depth. Case number 2 is Y0 is less than YC, or the normal flow depth here is less than critical flow depth. And case number 3 is Y0 equals to YC, where the normal flow depth equals to the critical flow depth. There are even further two cases possible for which the normal flow depth doesn't exist, because the uniform flow is not possible at those for those cases. And those cases are case number 4, where the channel bottom slope is 0 or the channel is horizontal, so S0 equals to 0, and case number 5, where the channel slope is adverse or S0 is negative. So these are the broadly the 5 cases possible for gradually varied flow, and for those 5 cases we can draw a couple of imaginary lines in the longitudinal section of a gradually varied flow, and those imaginary lines are the critical depth line or CDL and normal depth line NDL, and these lines divide the flow space in the flow profile into specific regions, where there is region number 1 is the flow space above the topmost line, flow space between the topmost and the second line, and the flow space between the second line and the channel bed. This will become more clear with the diagram representation of the same. Now this table actually shows that on the basis of the 5 cases that is enumerated above, was enumerated in the last slide, open channels are classified into 5 categories, and those categories are based on the type of slope and the flow conditions. So case number 1 is the channel category of mild slope, which is symbolized by M, and the characteristic condition is where the normal flow depth is greater than the critical flow depth. So this represents the subcritical flow condition at normal depth. Case number 2 is the steep slope, belongs to the steep slope category, and which is symbolized by S, and this is the condition. This is the case where the normal flow depth is less than the critical flow depth, and which signifies or implies that the flow is supercritical at normal depth. Case number 3 is the case of the critical slope. The channel is at critical slope and is symbolized by capital C, and here the normal flow depth equals to the critical flow depth, and of course signifies critical flow at normal depth. Case number 4 signifies represents the horizontal bed or zero bottom slope channel, and which is symbolized by capital H, and the condition is S0 equals to 0. So as we discussed before, this type of slope cannot sustain a uniform flow. Similarly, case number 5, which is the case of the adverse slope of the channel and symbolized by capital A, where S0, the bottom slope, is negative, and this case as well, this type of channels as well cannot sustain a uniform flow. So this slide is the pictorial representation of all the 5 cases that is that has been discussed in the last couple of slides. Here we can see the longitudinal sections of channels of different categories, and the couple of imaginary lines, NDL and CDL, we talked about, and the flow spaces symbolized by 1, 2 and 3, which represents the regions or the flow spaces as discussed in the last slide. So here for case number 1 is the case of the mild slope channels. We can see that the NDL is above CDL, and there are 3 regions, 1, 2 and 3 of the flow space. Here the channel bottom slope is positive. Case number 2 is the case of the steep slope channel, where again there are 3 flow spaces, 1, 2 and 3, and the channel bottom slope is positive. But here note that the critical depth line or CDL lies above the normal depth line or NDL. Case number 3 represents the critical slope channel. Here of course the CDL and the NDL are coincident. They are coincident lines, as the critical flow depth and normal flow depth, they are the same. So here there are only 2 regions in the flow space possible, 1 and 3. Flow space number 2 is absent here. Case number 4 is the case of the horizontal bed channels or zero bottom slope channel. As we discussed that here uniform flow depth or normal flow depth is not possible. So the imaginary line of NDL is non-existent here. Only CDL exists, or so in this for this case there are 2 regions only, region 2 and region 3. Note that region 1 is absent here. Case number 5 is the case of the adverse slope, and here also the uniform flow is cannot be sustained, and so there is no normal depth line possible, and only CDL exists again, and the flow space again is divided into regions 2 and 3. Region 1 is again absent for this case. So that's all for this lecture. We will talk more about gradually varied flow in the next lecture. Thank you very much.